Okay, everybody. Here is our first problem in the next section. So this is actually section 5 of chapter 18 for those of you playing at home. Now, in a lot of ways, these aren't any different than what we started doing already. And just sort of refresh your memory, we're talking about kinetic energy coupled with rotation. All right. And our go-to in all of these things, I don't like where that is. Our go-to in all these things is going to be our friendly old energy equation, which we've used many times before. And it's back to help us out here, which is to say that delta K is a minus delta U plus work. All right. So we're saying here that the kinetic energy change depends on the negative, some potential energy change, and then whatever's work is done. Now, all that's different, you can see we just added the delta U term, okay? And just keep in mind that you can really use either delta U or W for work. Just don't do it with the same force, okay? So we could have gravity operating on something, it falls down. We could think of that as work from gravity, or we could think about it as a potential energy change of gravity. We just can't do both because then we double count, okay? So in our case here, what we want to do is we want to put our pivot in sort of the natural place right here. And so we're going to actually need the moment of inertia about the pivot point, which is going to be our geometry term, 1/2 mr squared, and then our parallel axis theorem term, which is our md squared. And this is another one of those cases where r is d, and so actually it turns out to be 3/5. But when you run the numbers on this thing, your moment of inertia is going to be 4.05. Now I'm going to go a little bit faster on some of those details because by now you got the hang of how to do all this stuff. So I don't want to burn up time doing that, but make sure you go through that with your own numbers, okay? All right, our kinetic energy, we're going to do this all in terms of rotation. So we're not going to have the translational energy in this thing. So that's going to put us just with 1/2 the moment of inertia, omega final squared minus omega initial squared. And that's a minus sign there. This is minus mg delta y. All righty. Now our initial angular velocity is 0. So that term is gone. Let's figure out what the change in potential energy is. So we've got mass, which is 30 times 9.81, and our delta y, okay? So in this particular problem, it turns out we have started at theta equal to 0, and that basically means that this thing was sitting here like that, just sort of stuck straight out from that thing, and it's going to fall all the way down here like this. And so our ending height and our beginning height are right there, and so our change in height there is just the same as the radius, so that's going to be 0.3. So we've got 0.3 in here. All right. Now, we started high, we ended up low, so that's a negative change there. And that's to be expected because we want this thing, as it falls, its kinetic energy should increase, not decrease on us. So we get that there. And the change in kinetic energy then becomes 88.29, like so. And of course, that's joules. Now that's just the right-hand side of the equation. Our other side is still the 1/2 I naught omega final, and which means we get the same relationship that we're used to seeing in all of this, which is omega final. It's the square root of 2 onto 8829 divided by I0. And when you run the numbers on that, then what you're going to get is 6.603. Okay, and of course that's radians per second. Okay. Now, this general pattern we're going to be following for all of these other ones. And so if that makes sense, if you got that, you're in great shape, okay? Okay, here's the next one. That one seemed kind of short. I thought I'd just throw this one on here too, because it's going to be pretty much equally short. Here we've got a reel, it says, and gives us a radius of gyration. Released from rest, all right, determine the angular velocity when its center O has traveled 6 meters down the incline, okay? All right, what's peculiar about this question, though, is you see where the rope is attached. We're going to have some tension here working backwards on it, okay? Now, it says it's a smooth inclined plane, so this thing, it could slip on us. We don't know. Since it could possibly slip on us, that means we really don't know the relationship between the rotation and the translation, okay? If it was not slipping, then we could use that relationship and we'd have some other options to work with, but we are not guaranteed that in this particular case, all right? But whether we have that or not, then what we could do is we could pick this point right here. Let me call that A. And that is our instantaneous center of rotation as this thing is traveling. And that actually makes a pretty nice place to work from, thinking about it pivoting and thinking about this thing sort of moving. I mean, it's not moving in an arc, but to combine the translation and the rotation this way, which is the nice thing about the instantaneous center. So we get rid of that thing right there. And what we're going to do is we're going to need the moment of inertia around A. So we're going to need I sub A. And so that's going to be the geometry term, all right, which since they give us radius of gyration, we've got that there. Then our offset term is going to be m d squared, okay? And so be careful there. D is actually 0.2, okay? And the radius of gyration, of course, is 0.3. They tell us that. All right. So read it pretty carefully. Don't take it for granted. But when you do calculate that, what you're going to get is 6.5, which is hilarious that it worked out to be so nice and neat. But nonetheless, there it is. Okay. Then we go back to our lovely energy relationship. Okay. I want to get rid of that. Didn't like that. So we're going to be looking at our delta K. It's minus delta U plus our work. Okay. Now, in all of our examples today, the work term we're going to toss. Okay. When would you not toss that work term? You would not toss that work term. You would keep it if you had some friction and you had to account for losses due to friction. Like something was sliding, you know for sure that it's sliding, there's some friction, then you need that work term to take care of that. All right, now since we picked it at A, instantaneous center, we're combining the rotation and translation into single terms. So we've got 1/2 I at A onto omega final squared minus omega initial squared. Okay, and so we got rid of this work term here. Ooh. Huh, that's weird. It doesn't want to write up there. Sorry about that. Made a mess of it. All that's going to 0. Okay, and so we don't have a spring here, so we don't have spring energy. All we have is displacement due to gravity, so we can do gravitational potential energy, so minus mg delta y. Okay, so let's think about delta y for a second. Okay, right now we're at some height here, and it says it's going to travel 6 meters down, so the center of mass is going to move down to some new level, and we know that that distance is 6. That's 30 degrees, and so if we run all that together, then you can see that our delta y term is going to be 6 sine 30 degrees. Okay, and it's negative once again. Okay, actual value for that is minus 3. Okay, so we got minus, coming back over here, it's 59.81 minus 3. All that works out to be 1472. And so we're going to get back omega final square root of 2, 1472 over I at A. So the final angular velocity is 21.3. Okay. Assuming we're starting from rest, which it says we are. Okay. There we go. So you see in a couple different contexts there, and all that we had to rely on in that case was just a change in position with respect to the weight, or with respect to the Earth. Okay. All right. There we go.